Hey guys, welcome back. So, in the last episode, we talked about things like oscillation, vibration, sine waves, frequency, crests, troughs, zero crossings, compression, rarefaction, wavelengths, frequency, hertz, kilohertz, all sorts of things. Today, we're going to cover things like amplitude, SPLs, decibels, phase, complex tones, pitch, the harmonic series, and we'll begin with a recap of the last episode. All that and more in today's episode of Music Mechanics. Notice how the crest and troughs are displaced further from the zero crossing as the sine wave gets louder, and also how they get closer to the zero crossing when the sine wave is softer. The distance from the zero crossing to the top of a crest or the bottom of a trough is a measure of amplitude. At this point, we should note that some of the terminology previously mentioned differs from recording engineers to musicians. An engineer might refer to a sound as 440 Hz, while a musician might refer to the same sound as the musical note A4, the 4 being a designation of which octave the A is played at on the piano. Additionally, what is referred to as amplitude by a recording engineer might be referred to as volume by a musician. Amplitude is measurable through the amount of sound pressure exerted onto the air. In other words, sound pressure is the difference between the average local undisturbed pressure, also known as equilibrium pressure, and the pressure in a sound wave. Incidentally, sound pressure can also be exerted onto other mediums like water. The sound pressure level is identified with the shorthand SPL, and the agreed-upon scientifically measurable unit is called the decibel, or dB. The decibel was named after the father of telecommunications, Alexander Graham Bell, and was used to measure transmission efficiency and signal loss in telephone and telegraph lines. If we look back at our previous example and zoom out, you will note that what we are seeing is really just a representation of pressure and time. The vertical axis of crest and troughs are recorded sound pressure waves, while the horizontal axis is the passage of time. The number of waveforms that pass a given point per second represents the frequency. An interesting phenomenon happens when you take two sine waves of equal frequency and amplitude, play them at the same time, and match the crest and troughs of the two waves exactly. This is called being in phase with each other, also known as constructive interference, and the combination of the two waves in phase doubles the resulting amplitude or volume. We will test this using a meter that measures amplitude. Even more interesting than constructive interference is what happens when you line up the two sine waves so that the trough of the second wave is lined up perfectly opposite of the crest of the first wave, a phenomenon known as being out of phase or destructive interference. In this case, the resulting combined amplitude of both sine waves is zero. They literally cancel each other out and produce no volume. It's referred to as phase cancellation. Let's test this now. You might have heard of sounds being out of phase before. In real life, they do not fully double or cancel since the two sounds must be of equal frequency and amplitude, extremely difficult to do in nature. So the resulting combined sounds are often slightly louder and fuller or softer and thinner. There are also other factors like overtones, which we will discuss later, that further complicate things. Up to this point, we have been dealing with the absolute simplest of sound waves, the sine wave. Certain electronic instruments like synthesizers can produce a single pure sine wave. However, barring these electronic instruments, virtually all instruments produce multiple sine waves at once per each sound played. In other words, every time you hear a single sound coming from a single instrument, you are actually hearing multiple sine waves at once. They are called a complex tone, as opposed to a simple tone, since a simple tone, a pure frequency, is a single sine wave, while a complex tone is multiple sine waves combined and occurring at once. To illustrate this, let's use the simplest of examples, a string on a string instrument. When the string is at rest, not being played, it is at the center point of equilibrium, or zero crossing if you will. If I pluck the string, it will vibrate. Notice how the string is now oscillating between the left side and the right side of the equilibrium point. Let's slow this down even further so you can see it better. What you are seeing is what's called the fundamental frequency. This fundamental frequency is what musicians would call the pitch, or relative highness or lowness of the sound. What's actually happening, though, is the string is producing multiple frequencies at once due to multiple sine waves simultaneously vibrating along with this fundamental frequency. Each one of the sine waves playing along with this fundamental frequency is called a partial. The fundamental frequency is the lowest partial, and it is the easiest to observe with the eyes. It oscillates over the entire length of the string. However, if you were to put a strobe light on this string and set it to strobe at different speeds, it would show the other partials as well, depending on which partial was oscillating in sync with the chosen speed of the strobe light. In other words, the string is not only vibrating its entire visible length, but it's also vibrating in halves, in thirds, fourths, fifths, and so forth, all while simultaneously vibrating along its entire visible length. Examples of this can be seen at the links given in the description section below the video. Take the time to visit these links. They are truly fascinating and beautiful. Each of these partials are simple sine waves or pure tones that, when combined together, make up a single complex tone. Each one of the sine waves or partials in a complex tone has its own frequency, phase, and amplitude, which greatly, though not entirely, makes it possible to distinguish the sound of one instrument from another. The partials in a complex tone are organized into what's called a harmonic series. After the fundamental partial, each succeeding partial in the harmonic series is divided into increasingly smaller and smaller equally divided parts, or integer, whole number, not fraction, multiples of the fundamental frequency. So, looking at the fundamental frequency which spans the entire length of the string, the next partial in the harmonic series we would see is the string oscillating in two equally divided oscillating sections, then three equally divided oscillating sections for the partial after that, then four equally divided oscillating sections after that, and so on. This is demonstrated in this diagram. These partials are also synonymous with the terms modes or harmonics. Any partial which is not the fundamental frequency can also be more specifically referred to as an overtone. When a string is played, each mode in the harmonic series divides the fundamental frequency, seen as the entire length of the string, into 2, 3, 4, 5, etc. equal-sized parts. The smaller the part, the higher the frequency. So a mode that divides the string into 7 equal-sized parts will produce a higher frequency than a mode that divides the string into 2 equal-sized parts. The fundamental frequency is also considered a harmonic since it can be multiplied by itself. The wavelength for the fundamental frequency is twice the length of the string, since the string must have a compression and rarefaction phase to complete one cycle. So the harmonic series would appear in this order as divisibles of the fundamental frequency. For those of you who are musicians, here is the harmonic series as it might be represented in music notation. The harmonics that are found at the red notes in this example are somewhat out of tune from what we are used to hearing. This is because the harmonic series as it naturally exists is different from the westernized system that we use today, otherwise known as equal temperament tuning. In equal temperament tuning, an octave is divided into 12 equally spaced pitches. This is the Western chromatic scale as we know it, and it is somewhat out of tune with some of the harmonic series as it naturally exists. The 7th and 11th, for example, are out of tune. So as a last-minute way to wrap up, I thought I'd try a little experiment with my bass. I'm going to play my open G string and then play each succeeding harmonic to see just how out of tune they are with our equal temperament tuning system. For you musicians out there, here are the pitches being played on the staff at concert pitch. Equal temperament, as mentioned before, divides an octave into 12 equal portions, with each portion being exactly 100 cents. 1 cent being a measurement unit of 1/1200th of an octave. Earlier tuning systems, such as just tuning, were based on the ratios from the harmonic series, but proved to be inadequate for keyboard instruments in all the various keys. While string and brass players can immediately adjust their intonation, tuning to each other, keyboard instruments afford no such ability. So the equal temperament tuning system was created to allow keyboard instruments to play equally in every key with the minimum amount of errors in tuning. So let's check this out. First is the fundamental. Now, as you can tell by the 0 below it, the G is pretty much spot on. Let's see how the next harmonic is. That's the second harmonic. Of course, that's a 0 too. That looks good. D also is a 0, third harmonic. G again, 0. Spot on. B is minus 13, that's quite a bit off. D is off by 1 or 2, minor discrepancy. The F is off by about 30 cents. The G again is pretty much spot on. There's zeros and ones. The A is about 4. Again, minor discrepancy. The B is again about minus 12. The C doesn't really know what to do with it. It's kind of all over the place. Thanks for watching the video. Be sure to like and leave a comment below. And don't forget to hit the subscribe button. If you like what you're hearing, be sure to pick up a copy of Michael Levan's new CD, A Different Shade of Blue, at this link. Until next time.